Good morning, everybody. I'm very pleased to be here. Thanks a lot for the kind invitation to this wonderful event. I've already been here last year, and I enjoyed coming back to Riga for this nice event. And what I want to talk today about is a little bit about the developments that we have at the high end, where we talk about exascale computing, which is the next big thing in high-performance computing. But actually, I want to frame this a little bit in the context of what it means to all of us. Because you might think that exascale computing is something that, well, there are the few big guys that do that. I don't really need to worry. I hope that after this talk, you will worry and you will do the right actions. Okay, so why do we talk about massive computing at all? Well, the reason really is that science fundamentally has evolved from empirical, theoretical, but now computational and data-based science. Right? So, as it was just said, the combination of computing power and data, this is really where the future will be. And we also call this e-science in some contexts. And this is really the push from the scientific side to invest more into high-performance computing, data processing facilities, and so forth. And of course, this push comes also from industry, pharma, oil exploration, energy, economics, social industries. Think of all the data that you have available via Twitter, Facebook, and so forth. So there is basically this e-science combining compute and data is everywhere. If we talk at the extreme scale, it's really this integration, combination of different data that is making new science possible, like here in the life sciences, where you go from genome to molecule structures and images. You integrate everything, you simulate everything, and you need extreme compute power to actually do all that work. In the life sciences, one of the most challenging projects clearly is the Human Brain Project that tries to develop a better insight. I would not say simulate the human brain, that's probably going a little bit too far, but develop better insight in how the human brain works, with the hope that that actually will also end up in cures for some brain-related diseases. And what basically this shows, where we are here at the moment in the petaflops area. So we are somewhere here that covers basically the complexity of a rat brain, which can be very interesting to study. And some people believe that the rats are really the rulers of the world anyway, because they will survive whatever we do. But still, we want to push it further, right? We want to go to the human brain. And that's then something that really requires exascale power. So yet another order of magnitude more than we have today. But as we are here at Riga Technical University, it's an engineering university. Even in engineering problems, we are approaching this problem. So this is the direct numerical simulation of a typical wind tunnel experiment that you can probably do with 1 million of cores, doing some 10 months of simulations. That's pretty okay. That we can do today. That's the petascale. But if we really want to go into direct numerical simulation of a real aircraft, of a wing of an aircraft, I'm not talking about full aircraft, then we need exascale. So we have challenges that are becoming even larger and larger, and we want to do more in silico because obviously also it's very expensive to build those wind tunnel experiments. And for these we need extreme compute power. And the systems are growing, right? This is the largest system that we currently have in the world. This is the Dianhe 2 system in China at NUDT that delivers a 55 petaflop. And there is an attempt to really go into the next level, exascale, meaning 1,000 petaflops, right? And Japan was the first country that really announced a roadmap towards exascale, but certainly also the US are running, and probably China are running as well, although we don't know that much about that. And if you look at the trend, then this is the top 500 list. This yellow line here shows the largest systems in the world. And if you extrapolate this, then indeed by 2020, just following this historical development, we should be there at an exaflop. You see very well this is really a step function. So several years you have one system being on top and then the next system comes, right? It stays like that. The other lines that shows the number 500 on the list, and this shows the aggregate performance. So summing up the performance of all 500 systems that are on the list. And what is interesting is you see that these curves are kind of flattening. I would guess this is not a technology issue that they are flattening, but that's the impact of the economic crisis. At the end, particularly when we are at this scale down here, and this of course influences a lot what is happening here, is how much money do people have to buy large systems and how many large systems are being bought. So you actually see here an impact of the economic development on the development of supercomputers. But as I said in the beginning, this is all nice, and this is always good for the big guys, people who love the big systems. We know there are specific important problems, but not everybody is going to work on the Human Brain Project. Not everybody is going to do a full simulation of an airplane wing. Not everybody is doing climate simulations. So most of the science that we do today is actually done at the petascale, even at the terascale, and sometimes even at the gigascale, meaning your computer, yeah, your workstation, your desktop that you have in your office. And that is providing a large fraction of the science that we do today. So why are we discussing this here? Yeah? Sweden will not buy an exaflop computer. Latvia, I don't know, but I would also have my doubts that by 2020 Latvia will have an exaflop computer. So why should we care at all? Yeah? Let's let the US and let Japan do it, and we just do what we do, what we can do, what we can afford, and where we're good in. The problem is that the quest for exascale, what is happening here is really cruelly exposing the key problems that we have with our current approach to computing. And this is affecting everybody, whether you compute on your desktop, whether you compute on your department server, whether you compute on a national HPC system. We will all have the same challenges. I'll try now to discuss some of these challenges. You probably all know about Moore's law, right? Which basically says that the transistor density is doubling every 18 months or so. And Moore's law has been paraphrased that performance is doubling every 18 months, every 2 years or so. And we've all been happily believing that. Yeah? But now you hear more and more people saying Moore's law is over. Yeah? It's not there anymore. But that's not true. Moore's law is continuing, yeah? So far. Of course, there will be an end to it because we will come into dimensions that are really not handled, from a physical standpoint, not possible to handle any longer. But if you look at the chip development starting from the 1970s up to now, so this is Ivy Bridge, the previous generation of the Intel processor, we have more transistors on the chip, really following Moore's law. So where's the problem? Well, the problem is that people have taken the wrong interpretation of Moore's law. Previously, while we were down in this area, up to 2010, 28, something like that. It really meant that with the increase of the transistors, so this is the transistor curve, yeah, that you saw before, Moore's law, scaling perfectly according to the expectation. But what we were able to do at the same time, we were able to increase the frequency, yeah, almost at the same pace, and we were able to increase the single thread performance by making more intelligent processors. What this in turn, of course, also meant that the power consumption went up, because it's all related. Now, as I said, around 2008 or so, we kind of hit the power limit. Yeah? It was not feasible any longer to provide more watts into the CPU. The way how to limit the power consumption was basically to limit the frequency. Right? So we see that now the frequency basically has come with this 2 gigahertz, some maybe go 3 gigahertz, but that's about it. You don't see a 10 gigahertz processor, right? And what that means is that performance basically stalls. If you don't increase your frequency, you get more transistors, but you cannot do more work, essentially. It also means that the single thread performance right-off stalls. But we're still getting more transistors, but how do we get them? Well, we, or the hardware vendors, invented the multi-core systems and the many-core systems. So they're still putting more transistors on the chip, but they are not usable as a single chip any longer, right? They're putting essentially many different independent chips on one single die. So Moore's law is continuing, yes, but we hit a power wall that does not allow us to increase the frequency any longer. And the power problem, if we go to extreme scale, is even worse. And you will notice that in most computing conferences, it's less talk about computing and more talk about energy efficiency and power consumption. So what you get today is about a gigaflop per watt. The most power efficient systems even around 2.5 gigaflop per watt. So this equates to some 400 kilowatt, 1 megawatt per petaflop. Just to give you an example of what that means, in my center at KTH, our power consumption is around 800 to 900 kilowatt, and we are having a yearly energy bill of around 11 million Swedish krona, which is, depending on the exchange rate, some 1.2, 1.3 million euros, which just goes into the energy bill. Think how many PhD students you can hire for that money. Yeah? So there's an issue, right? And if we go to an exaflop, it will be even more, right? Today, if we just take a machine today and we would build an exascale machine with today's technology, we are somewhere between half a gigawatt and a gigawatt, which is 1/3 of a nuclear power plant that we have. So it's clearly not possible, right? You will not put a nuclear power plant next to your computer. That's somehow out of proportion. Yeah? When DARPA in the US did a study, back I think it was in 2007 or so, they said, okay, what would be needed to go to exaflop? They said, well, max, we need to reach 50 gigaflops per watt, yeah? Which would still equate to a 20 megawatt computer, which would then still equate to some 15 million euros energy bill per year. Yeah? But this is what people believe for the high end, say in Japan, say in Oak Ridge, will be feasible. And indeed, it's the centers are putting in place appropriate power supplies to go up to 20 megawatt. That's the kind of aim they have. But this still means that we go from somewhere around 2.5 to 50. So 20 times, 30 times improvement is still needed. In 5 years, that's a challenge. We'll see. There is lots of work going on. We'll see where this ends up. But I want to come back what I said before. This energy wall we are running into basically means that we're still able to increase performance, but we increase performance through addition of parallelism, through addition of multiple cores. This is our current infrastructure that we have today. That's our Cray system that has Intel Haswells with 16 cores. And the CPU only has about 4 gigaflop per watt, which then for the full system goes down to 2 gigaflop per watt. And then you can have high-end graphic cards, which we have in another system thing near, which is a cluster, also based on Haswell, but also has GPUs in it. They're, of course, about twice as efficient, but then you see they're having about 5,000 cores. So it's an extreme explosion of parallelism. And that you see also in this graph down here, where the blue line is the single core performance that basically stays pretty much stable. We have here, it's going up a little bit. I think, great, it's at least some improvement. No, this going up is because they have introduced vector processors again. And now we have vector units, which again, you need to do something on the programming side to actually exploit them. But the performance increase of the systems really, they comes through multiple cores. So, what have we learned? The free ride is over. We cannot just sit and wait and say, well, I buy a new computer, it will be more powerful. Yes, it will be more powerful, but it will not be more powerful for free. Because the increased performance that we get, we will only get through increased parallelism. And this parallelism, this is really becoming ubiquitous. Whether you have the chip in the supercomputer, or you have the chip in your desktop, or you have the chip in your mobile device, there is different levels of performance that they have, of course, but they're all working against the same power wall. Mobile devices even more so, right? Because they need to be even more power efficient. So if you want to continue to be on an efficient side, you need to start thinking parallel. You need to start thinking, doing things in an efficient, parallel way, like the old HPC guys have been doing in their little corner over the past couple of decades. So if you have not done your classes in parallel computing, which I hope RTU is offering, then please go sign up now. It's really time that you understand this. Because whatever you do, you will need that. So, that's in a nutshell the discussion of the CPU. And for a very long time, we would have stopped the talk here. We said, what do we talk about? We talk about CPU, how many operations can we do in a second, in a minute, whatever. How efficient is my program? Now, as we go to the scale where we are today, and I'm not meaning now really the scale of the big system, but even the scale of a single processor, the development of a single processor. A CPU and the flops are still important, but they are becoming less important than they have been. We need to start thinking much, much more about how we deal with data on the system. Previously, we basically only said we want to minimize the operations. If we have less operations in our program will be more efficient. the truth really is that you need to minimize data movement. We are now having very, very deep memory hierarchies from registers, different levels of caches, memory. Then, of course, if we cross the system's boundary, then it's getting extremely slow, obviously, as we all know. But even within the system, right, there is difference between 1 nanosecond and 100 nanoseconds, right, sometimes. So there is a huge difference on where data is, and this is becoming actually more complex with the introduction of even further layers. You might have heard of storage class memory, non-volatile memory, which will or is already around and will be sitting somewhere in between here. Yeah? So we need to think more of how our data is being moved around. And you see this very, very clearly when you look at the energy consumption. So these are two curves, energy consumption 2008 and projections of 2018. Yeah? So this is the flop performance, yeah? And how much picojoule you consume for that. Flop performance between 100 and 10, right? So there is an order of magnitude that the efficiency, energy efficiency of chips actually has improved. There is some improvement when you go on the registers and chips, yeah? Then you're around here. But as soon as you are just 5 millimeters on the chip, it's basically the same. There's no performance gain anymore, and you use as much energy as you use for your computation. Yeah? If you go 15 millimeters on a chip and the chip is going larger and larger, yeah? You are up here. You're back in the good old times. And if you go off chip, of course, it explodes, right? So there is a big, big issue that we need to make sure that we are more in this scale here to be efficient and less over here. Yeah? And then if we are here, yeah, we can do 10 times as many computations, yeah, than moving the data. So we are entering an area now where we say, okay, let's do more computation maybe, but let's not move data. Yeah? Let's think about that. So this is the second item that is changing and that we have to think about. And again, we are discussing this in an exascale context. But there is no exascale machine in here, right? This is just one single system that you all are computing on. And finally, we have dynamic behavior everywhere. We basically learned that if we do parallel computing, we distribute our workload as even as possible, yeah? Which is a good thing to do. That means good performance. This is still true, but we have to understand that there is a wide variety in what performance a CPU delivers that you actually can't influence, right? CPUs are very dynamic today. They use dynamic frequency scaling, yeah? So if a factor of 1.2 to 2.5. Yeah? And this depends a lot on the workload, it depends on the heat, it depends on where the CPU is on the system, what is in the surroundings, and so forth. And we have the memory hierarchies that go actually make things worse. And this is something, this dynamic behavior, yeah, is actually something that even Google now starts to rediscover, where they have figured out that, yeah, what is the probability to keep a 1 second service level response, yeah? If you have systems that have varying frequencies, yeah, which you have today. And then, of course, if you have 1 in 100, yeah, where you have an outlier, then of course you very quickly, as the number of servers increase, you very quickly say, okay, we can't keep the service level any longer, yeah? So they need to invest into huge, get 1 in 10,000 actually to be manageable. Yeah? But that's very difficult. So system noise, various scaling, contention, all these things are coming back and making life for us very miserable. And that's something where we need more adaptiveness in our programs. So, that's the new computing world. Increased performance through parallelism. Data locality is probably more important than the reduction of operations. And we have to deal with dynamic computers. Yet, what do we do today? We run every computer, every node of a system as a single computer with a Unix-like US. We manage our data transfers, probably MPI. We use Fortran C, C++, and some exploit shared memory and threads and so forth. So it's a very static way of how we compute. It's still a kind of, we worry about cycles, we worry about flops, not so much we worry about the data. And we are really we're dealing with algorithms, yeah, that have not been designed with parallelism in mind. Yeah? Parallelism, that comes as an afterthought, it's an implementation detail. But parallelism is everywhere. We need to start thinking what algorithms can we have that support the kind of parallelism that we need, that support the kind of dynamic behavior that the systems have. And this is really something that is now affecting everybody. Yeah? Without fundamentally changing how we do computing, we will be stuck. Yeah? We will not be able to take advantage of future performance. We will be at the level where we are. So let's try to put it a bit here is that we will have codes that will not run efficiently on a laptop any longer. They will run, and you might be happy, but you will not be running very efficient, and the people giving you the money for your infrastructure will not be very happy if you don't use the potential of your infrastructure. So what do we need to do? We need basically to rethink how we do computing fundamentally. We need to start rethinking the algorithms. We need to start thinking, how are we programming the systems? How can we get more intelligence into the system at all so that we can deal with dynamic system? We need to think then, how are we going to implement it, and eventually also what's the choice of system? Yeah? We are seeing now a wide variety of different hardware coming. Yeah? We have the classical Intel CPUs, we have the accelerators, we have the mics, we have the ARM processors, we have Open Power, we have Spark. So we are back in an area where there is many, many different systems, and not each system is equally well suited for every application. So we need to start thinking here more as well. So I want to end my talk with just telling you a little bit what we do at KTH to address those problems and what we do in the Exascale arena. So we have been partners of some of the flagship projects in FP7. We are a partner of a project called Questa that basically tried to look into those aspects in a co-design fashion for several applications, and we focused on GROMEX, which is a molecular dynamics application, and NEC 5000, which is a spectral element CFD application. So here we try to understand what's the behavior of these codes, what are the limiting factors, how can we improve them on current architectures, but what would also be needed to go beyond current architectures. We have another project called Epigram, which then goes more into the programming models. As I said, what are the implementations? What are the programming models that we need? Will it still be MPI? Do we need something else? What will it be? In Epigram, we're particularly looking into MPI because we believe that in whatever form, there is a need to do message passing, and MPI will be a basic building block of whatever future large-scale computer we are building. And so we are addressing the scalability issues of MPI and also looking into PGAS models. But recently, now there has been a big focus of the European Commission on exascale computing. Yeah? There was recently a call on future emerging technologies focused on exascale HPC technologies and focusing essentially on the 4 items that I presented you before that we need to work on. What are the algorithms? What is the systemware? What is the programming models? And what is the systems? What are the computers, the architectures that we will be running on? So that's the good news. Europe is taking this seriously, yeah, and has started now a set of projects, or will start a set of projects in all these. And we are engaged in several of these projects focusing on mathematics, programming models, and core technologies. Most of these projects will start in autumn. So that's just the examples of what we will be working on. We are coordinating a project called Exaflow that deals with fluid dynamic simulations, and I'm telling you a little bit more about this in a minute. We are looking into memory hierarchies, non-volatile memory, storage class memory with Seagate. Yeah? What will be the future memory architecture? As I said, this will be a very important thing, and particularly then how to deal with this new memory hierarchy from a programming point of view and from an application point of view. Yeah? We're looking together with EPCC in Edinburgh on programming models interoperability, because it's very likely, given the huge heterogeneity of hardware, that we will not have one single programming model any longer. Yeah? And we are looking at extreme scale programming exploiting nested recursive parallelism. So kind of a different approach, completely different approach on how you look into parallelism. Exaflow, which is one of our flagships that we are coordinating, that tries to address algorithmic bottlenecks in fluid dynamic simulations. Yeah? So we're looking here particularly into adaptiveness, adaptive mesh refinement. Remember what I said before? Dynamic features, that will be very important. And we look into error control, algorithmic error control. How can you keep the error in your algorithms under control? Of course, the usual solver efficiency. And here I say that probably it's not a single solver that you will use. You will use hybrid approaches, applying different solvers depending on different architectures and different problem domains. So we will look into discontinuous and continuous galerking methods particularly. We'll look into fault tolerance and resilience on the algorithmic level. Yeah? Heterogeneous modeling, parallel I/O, and energy awareness. So again, so you see it's always the same theme, right? How do we deal with dynamic aspects? How do we deal with data on the system? How do we deal with heterogeneity? And the final thing that I want to mention, which is not so much an aspect of moving towards exascale, but having a wider impact of all these developments we are having, is what is called Centers of Excellence. That's a new instrument that has just been started, which is an instrument to aims to improve access to applications and expertise. Right? Help people better finding the right application, finding the right resources, solving the problem in the most efficient way. And we were lucky to win one of those centers of excellence in the life science domain. So it's called BioExcel, Center of Excellence for Biomolecular Research. And here we're looking into important software codes, GROMEX, Haddock, and CPMD for biomolecular research. And we'll look into efficiency and scalability of this. And we'll particularly look into the usability for researchers in academia and industry. Yeah? Making sure that actually the exascale work that we are doing is not just limited to a few small users, but we actually spread the word and the knowledge as widely as possible. That's a 3 years project. We'll start in hopefully November with a budget of 4.8 million euros. And we have partners from Sweden, Spain, Germany, the Netherlands, and the UK. And finally, we have inside Sweden, the Swedish eScience Research Center that works a lot on core technologies, yeah, and combining core technologies in parallel computing, in modeling, numerical analysis, visualization, with different scientific domains that are important for KTH, physical sciences, life sciences, and engineering. And actually, these interdisciplinary teams that we have built at KTH, they have been the nucleus to allow us to actually go further, to go into those Horizon 2020 projects. So that was or is a very, very important aspect of our work. So, where we will be going? Well, Exascale is coming. Yeah? Whether we'll have an Exascale machine in 2020 or not, that's still a debate. I'm a bit skeptical, but not so much about technology, more about the finances that would be needed to build this. But these developments, they really need us to rethink how we do computing and data analysis. We need to rethink algorithms, implementations. When we talk data analysis, I haven't talked about that, but that's another aspect. Do you do data analysis offline, or do you do it in situ? Most likely we'll move towards in situ because the data are getting way too big, yeah? That you can first do your simulation and then do the analysis. KTH is very actively engaged in this, and I hope we'll find some collaborations also here with RTU in some of these aspects. And that's our latest toy that we have just inaugurated in January. That's our new petascale resource at BDC that is combined with pre- and post-processing facilities, normal clusters with GPUs, and so forth. Okay, so with this, I hope I gave you a little idea on what are the challenges, where we need to focus on. I gave you some ideas on where you could focus your future research. And as I said, if you have not done your parallel computing classes, go sign up today. Thank you very much.
Thank you, Erwin. Please, any question, if we have time for questions. If there is no, I have a question. You know, Cisco changed the CEO after 20 years. And then it was a discussion how it will be in such a time. The new ones are be bold. I would like to ask you, what makes you bold?
That's a very difficult question. I think what we still need to see that what we do here, what we do on the computing side, we don't do for computing per se, right? We are not just burning cycles because we want to burn cycles. We want to do science, yeah? And I think if we can manage that we enable through our technology major scientific breakthroughs, be it new drugs, be it more efficient airplanes, being new forms of energy, yeah? I think that's the nice thing that to have, yeah? As a good friend of mine, Bill Kramer from NCSA once phrased it, yeah? He's not so proud about the systems that he's working on and that he has built and operated and supported. He's more proud about the Nobel Prizes that people won using those systems. Yep.
Thank you very much. Yep, please.
So you have shown in the previous slide, I guess, this in the middle, this system. how did you start it and how you will go on and proceed with this? It's a very good idea to have.
So basically what we try to do and what this figure tries to explain is that when we started this, we had activities at KTH that are the computer science activities, right? How we build new computer, how we program them, what is the mathematics behind it, and so forth. And we had the people doing engineering, life sciences, physical sciences. And they were not talking to each other, yeah? The computer scientists, they were doing their work, right? And then you had the center, which was different from the computer scientists. The center was providing the hardware. And those people were using the hardware, and we were just, as the center, talking to our friendly vendors and followed their advices and bought what they thought would be best for us, yeah? Of course, in a slight collaboration. So we tried to break this, yeah? Through an e-science approach, we started to employ what we call application experts, yeah? Which are people that have a good understanding of a certain domain, but also very good skills, that are able to actually employ the latest developments, yeah? Transfer the knowledge from here to out here. Yeah? And that started with this circ, which we did for the past 5 years. It's a long process. Yeah? It needs time. But we have very good success cases, and what we're trying to do now actually at KTH is putting that at the next level, that we're not only forming these interdisciplinary teams, yeah, working together, but we won't really have an organization where they can physically spend time together and sit together. So PhD students from the various domains, PhD students working on the computer science aspects, and people operating on the systems that we have, really spending time together, sitting in the same office, yeah? Exchanging thoughts and ideas very naturally. And of course, having also the senior faculty coming in every now and then. So, call this a scientific computing lab. That's the latest idea we have. We are discussing this at the moment. It's not implemented yet. But we believe that this is the next step forward that can help implementing this e-science vision, help forming these interdisciplinary teams, which are needed today.
More questions, please? Then thank you very much.
Thank you.